In 2024, something remarkable happened at an architecture firm, a moment that sent ripples through the profession worldwide. The design team had been wrestling for 3 weeks with passive house insulation optimization, balancing window placement to minimize heat loss, detailing thermal bridge breaks, and tracing airtight lines across a complex building envelope. Then I completed the same task in just 4 hours. What once required hundreds of manual simulation runs, each adjusted by hand, each requiring a wait for results, was replaced by a continuous loop of automated generative exploration, converging on the optimal solution without human intervention. This is not a vision of some distant future. It is already happening in architectural practices around the world. Today, we go deep into the frontier where artificial intelligence meets zero-energy building design, and the results are more dramatic than most architects expect. To understand why this convergence is happening now, we need to look at the regulatory and technical pressure building under the global construction industry. Governments across the European Union, the United Kingdom, and North America are advancing mandatory zero-energy building standards, many targeting net zero new construction by 2030 to 2035. Public buildings in multiple jurisdictions are already required to meet near-zero energy performance thresholds, and private sector mandates are progressing rapidly through legislation. The technical challenge driving AI adoption is not a simple one. Passive house design is far more than adding thicker insulation. It is a high-dimensional optimization problem: solar gain, wind exposure, thermal bridging, air tightness, ventilation, heating and cooling loads, and material thermal conductivity all interact in cascading ways. Change a single variable, and the entire system responds. A human designer manually iterating through these trade-offs faces hard limits in time and cost, and that is precisely the point where AI delivers its most powerful value. So what, specifically, does AI do inside a passive house design workflow? The work breaks down into 3 core domains. First, automated energy simulation. Traditionally, a designer manually entered dozens of parameters into software, such as Energy Plus, or IESVE, then waited for results before adjusting and repeating the cycle. AI replaces this with generative design. It auto-generates thousands of design scenarios, predicts the energy performance of each, and surfaces only the candidates closest to the target threshold. Industry data indicates that AI-assisted design review can cut simulation cycle time by approximately 40% on average. Second, automated thermal bridge detection. AI analyzes BIM models to automatically flag structural junctions at high risk of thermal bridging, then proposes remediation details. Pilot programs for AI regulatory review, such as Singapore's Cornet X system, have demonstrated the ability to flag roughly 92% of compliance errors before formal submission, dramatically reducing costly late-stage revisions. Third, climate adaptive optimization. AI ingests real-time local weather data for the project site and automatically calculates the optimal window-to-wall ratio and overhang depth for that specific microclimate. The designer's role shifts to reviewing, evaluating, and making the final professional judgment. Now let us look at the specific AI tools that are production-ready for passive house and zero-energy building workflows right now. 4 stand out in current global practice. First, Autodesk Forma. At the earliest design stages, Forma delivers AI-powered real-time analysis of solar access, wind conditions, and energy performance, all before a single wall is placed in detail. Its direct integration with Revit makes it a natural fit for BIM-driven practices. Second, Cove.tool, a cloud-based platform for automated energy modeling and carbon footprint analysis. Cove.tool has been validated on major international projects, including LEED and BREEAM certification workflows. It supports customization against a wide range of national and regional energy codes. Third, SketchUp Safari. For teams working in SketchUp, Safari provides instant energy performance feedback during concept design, the lowest barrier to entry of any tool in this category. No separate workflow is required. Performance data appears as you design. Fourth, Ladybug Tools. This open-source, Python-based platform has become the global standard for parametric environmental analysis. Built on Energy Plus and Radiant simulation engines, it integrates natively with Grasshopper and Rhino and is used by leading architecture and engineering firms worldwide for passive house energy modeling, daylighting optimization, and thermal comfort analysis. Across documented global projects, AI-assisted design tools have been shown to reduce the overall design period by approximately 40% on average. Knowing the tools is only the beginning. The real transformation comes from understanding how to structure a complete project workflow around them. Here is a 4-stage AI-assisted passive house process validated in real-world practice. Stage 1. Automated site data collection. AI ingests climate data for the project location, analyzes solar shading from neighboring structures using GIS datasets, and retrieves ground thermal conductivity values, a process that previously required hours of manual research and now runs in minutes. Stage 2. Generative massing study. AI auto-generates hundreds of building form variations and assigns a thermal performance score to each. Designers review only the top-ranked candidates, dramatically compressing the early massing phase. Stage 3. Automated thermal bridge review in detailed design. As structural drawings develop, AI continuously scans for high-risk junction conditions and flags them before they reach construction documentation, catching problems when changes are still inexpensive. Stage 4. Certification simulation automation. The final design is automatically run against zero-energy building certification criteria, with a gap report generated that clearly identifies any items falling short. Real-world implementation of this full workflow has demonstrated reductions in certification preparation time of approximately 58%, a figure consistent with findings from automated permitting programs such as Singapore's Coronet X, which reduced average processing time by roughly 60% compared to the previous workflow. A balanced view requires confronting what AI cannot do and where it can actively mislead. 3 risks deserve to be named clearly. First, data quality dependency. The accuracy of any AI simulation is only as good as the input data behind it. When airtightness performance, thermal bridge details, and actual construction tolerances are not accurately reflected in the model, simulation results and real-world building performance can diverge by 20 to 30%. This gap has been documented in post-occupancy evaluations of buildings that met simulation benchmarks but underperformed in actual use, a growing area of concern as AI-generated designs move into construction at scale. Second, creative bias toward historical precedent. Because AI optimizes from past data, design forms that break from established typologies tend to receive lower performance scores, even when they represent genuinely innovative solutions. Architects who follow AI recommendations uncritically risk converging on an ever-narrowing range of building forms, reducing the diversity and ambition of the built environment over time. Third, professional accountability remains with the architect. When an AI-recommended structural detail causes a problem on site, legal and professional liability stays with the licensed architect of record. AI is a tool, not a decision maker. That distinction is not merely administrative. It is fundamental to how these systems must be used. The stronger the tool, the sharper the professional judgment required to wield it responsibly. AI is dramatically lowering the complexity barrier in passive house design. Thousands of automated simulations, comprehensive thermal bridge sweeps, zero-energy certification runs. All of this is now achievable faster and with greater precision than any purely manual process could deliver. But as we have explored today, AI is not infallible. Managing data quality, critically evaluating AI outputs, and making the final professional judgment, these responsibilities have not diminished. They have grown more consequential. The more powerful the tool, the more decisive the expertise required to direct it well. Zero energy building mandates are arriving across global markets, in the European Union, the United Kingdom, North America, and across the Asia-Pacific region. The transition from voluntary best practice to legal requirement is already underway for public buildings, and the private sector is next in every major economy. The practices that begin integrating AI into their passive house and zero-energy workflows today will not merely operate more efficiently, they will be structurally prepared for a regulatory and market landscape that will increasingly reward precision, speed, and verified environmental performance above all else. The question is not whether this transition is coming. The question is where your practice will stand when it arrives.